Hello and welcome to another edition of Ontology Talk. I'm Adam Pease, and I'd like to do another video talking about different logics. I'm particularly concerned about logics that are implemented computationally as automated theorem provers. So first off, a little review. What is a logic? So a logic is a mathematical language for describing the world using symbols. And there's a syntax, obviously, that governs how those symbols are used. And there's also, more critically, a semantics that governs the interpretation of those symbols. It's common for me sometimes to talk about logic and get somebody to comment that, oh, well, I can just code that up, create a markup or a syntax for it. And well, the syntax is kind of the easy part. The problem is developing a mathematics that specifies how a computational system should interpret those symbols, and not just writing a program that does so, but actually having a mathematics that has a certain number of properties for it. So anybody can define a syntax, but how do you define the mathematics, and what sort of properties does the mathematics have to have? Well, at a minimum, to really be called a logic, it has to be sound, right? It has to be the case that if you say true things and you perform operations on those true things in the symbol system that you've created, that you don't wind up concluding false things. Okay, that's an absolutely critical property. And of course, notwithstanding Gödel's incompleteness theorem, right? So if you want to have a system that's sound, according to Gödel, it can't be complete. This doesn't really seem to come up in practice if you're doing, say, common sense reasoning or natural language processing. But I put it out there because certainly, if I didn't, a stickler would tell me that you can't have both those things at once, of completeness and soundness. So we don't aim for completeness. We just make sure that our systems are sound. So I want to show some common logics. There are certainly lots of talks out there on different kinds of logics. Very rarely do they contrast them with each other and say what the different properties are. I mean, I've even heard people say, oh, well, all logics are the same. Well, certainly that's not true. There are different mathematical systems that have very different properties. And it's also common to see talks about different logics that don't do anything computationally with them. They treat them as something that you'd write on paper, but in fact, there are computational systems that can do things with these logics, and so I'm really concerned about those kinds of systems. So I'm going to show some inferences in each of the logics that I introduce. And a lot of this content is also thanks to Professor Jeff Sutcliffe at University of Miami, the creator of the TPTP library of theorem proving systems, who also runs a yearly theorem proving competition. He created and has given, I believe in the past, some versions of this talk. I wanted to give my own version, and I hope he'll actually record his own version that I'm sure will have a different take and be complete in different areas. So let's start with propositional logic. If you have a STEM education, you've probably had at least some exposure to what propositional logic is, and it's a very simple logical system. You have statements about the world. So Bob eats an apple, it is raining, Mary's car is blue, and each of those propositions is represented by a symbol that can either be true or false. And in this language, you can also combine those symbols to say new things. You can say Bob eats an apple and Mary's car is blue. So if you give Bob eats an apple the symbol B and Mary's car is blue the symbol M, then you'd wind up with B and M, and that would be a new statement. It's all if the original statements are true, then the combination of those statements may also be true, and you can do problems. You can test these different operations and see if they all come out to be consistent. But propositional logic is a very, very simple system. It doesn't have any way to explicitly denote objects. It just denotes sentences. It says things that are true or false, but it doesn't have a way to say, for all things of type X, there's property Y, or you don't have any variables, and that's a critical limitation. So you've got a simple system. It has some very attractive properties and reasoning. It is decidable, and I'm not going to go into decidability here, but there's a reference if you'd like to do that on Wikipedia. And you give up a lot in terms of what you can say in order to have this very desirable property. And this is usually the trade-off. But there are some ways around this, and we'll talk a little bit about that. So let's look at a concrete example. So here is a kind of non-trivial problem. It's got 9 different statements about the world. So all the dated letters in this room are written on blue paper. None of these letters are written in black ink except those that are written in the third person, and so on. So these are each individual propositions. We can give them a name, and then we can test whether they're consistent with one another. Right? Ultimately we want to prove that the letters by a Mr. Brown cannot be read, right? Because that's one of the things we should be able to conclude. Right? I have not filed any of them that I can read. Right? So I've only filed ones that I can't read, for example. So these they're compositional statements, but they're very simple. There's no variables. They're just statements about the world. And you can encode this in one of the TP languages. So here is conjunctive normal form, CNF. I'm not going to go into great detail about this particular syntax, but hopefully you can look at it and see, let's say, the statement on the upper left. Either something is either it's dated or it's either it's not dated or it's on blue paper. Then either something is in the not in the third person, or it's in black ink. And these are also rules, because if I reveal the portion of the slide that's hidden by my video here, if you recall from your basic logic that A implies B is the same as not A or B, then all of these first 2 statements on the upper left are in fact rules. They're saying that if something is dated, then it's on blue paper. Okay, so it's just an alternate logically equivalent form. And so if you say all these things and then you have a conjecture, which is can it be read, then you can have a theorem prover like E or Vampire or many others within the TP system will give you a conclusion. But the point that I really want to emphasize here is there's no way to talk about any document that is in black ink, for example. We have a symbol in black ink that's meant to stand for a proposition. Something is in black ink. But we can't say in particular in black ink of X, right? A property is true of an individual or an object in the world because we don't have variables. So we're very, very limited in the things that we can say. And also, just a side note that this problem is due to Lewis Carroll, who's best known for writing Alice in Wonderland, but actually was quite a serious mathematician and logician in his day, and came up with a lot of very cool mathematical logic puzzles of this sort. So we can test this computationally. We can run it in the eProver that's written by Professor Stefan Schultz. And here's the command that I used, and on the particular problem encoding that I have, the problem encoding is taken from Jeff Sutcliffe's TP system. And you get a proof, right? And again, it's a little complicated. We don't have enough time to go into it right here. I'll do another video on how to read these proofs. It might look a little daunting at first, but it's really not that difficult. Anybody can learn how to do these if they have some basic background in logic. And it's a proof by refutation, so we assume the opposite of what we're trying to prove and then see if we can find a logical contradiction. If we can, that tells us that in fact the original axiom set is proved. So down at the end here on line C030, we get a $ false, and that's showing us that we in fact the system in fact has derived a contradiction. It has proved what we want to prove. And we can look over this justification and see step by step why it is incontrovertibly true. Each small step adds up together in this mathematically sound system to tell us that if all the things that we've said are true, then in fact it is undeniable that the conclusion is true. We can also display this sort of thing graphically. I have some little tools to do that. That really helps to understand proofs. Again, I'm not going to go into this proof in great detail, but I'm providing all the references here to how you can run these. If you download the E, Vampire, and Leo provers, we'll get to those latter two in just a moment. I should also mention description logic. So there isn't a description logic prover in Jeff Sutcliffe's system. It's an unusual class of logics that's been created somewhat more recently than some of the basic logics like propositional logic or predicate calculus. And it has some interesting things you can do, but also quite a lot of limitations. So you can talk about individuals, classes, and roles. There isn't a way to denote non-explicit objects. You only have binary relations. I have a talk on this channel about why you might want relations that are not just binary, such as between, and why it's a serious limitation to have that limitation. You can't negate, for example, an arbitrary proposition in description logic. It has some serious limitations. It's mostly a fragment or a subset of first-order logic. There are, however, some variants that are even arguably beyond first-order logic. It's designed critically to be decidable and tractable. Right? You've got a predictable behavior no matter what you ask of a system like this. And so there are some very standard reasoning tasks, such as subsumption, determining if one thing is a specialized version of another, and that can be quite useful. But you do give up a lot for these attractive computational properties. It's also the case that you can, well, it's arguable, but you can certainly make the case that the theorem provers for description logic are not as mature as the ones in the suite of TP-TP provers, especially first-order logic theorem provers. So I find that this claim that it's a good thing to give up the expressiveness in order to get more efficient inference is not as true as maybe it once was now 20 years plus after the initial flurry of interest in description logics. First-order provers like E and Vampire are incredibly powerful, incredibly fast, and so if you want a system that does have decidability, well, you always have the option of sort of taking stuff out, right? If you have a theory that's very expressive, maybe you can compile out or re-encode it as a less expressive theory and still use it with this same powerful theorem prover, and you'll get very powerful, very fast results. The issue about the speed has more to do with the problem that you give the prover than the prover itself. And Jeff's done some interesting experiments in this regard that show that on certain problems, the first-order theorem provers will just do better on the same data than your description logic provers because they're just more mature. They've had a lot more stress applied to them. So I want to talk next about first-order form. This is probably what most people work in, first-order logic, and it's what a lot of people's intuitions about what's possible in logic are drawn from, right? Very few people, unless you are a logician or working in this research area, have really done much outside of first-order logic. And so thoughts about, well, that contradictions, for example, are catastrophic is often, I find, drawn from an experience just with first-order logic in which contradictions can certainly be a very serious issue. There are still ways to handle them, and I have another video on this channel. I'll provide a link to that about how to handle contradictions in different logical systems. It's not as catastrophic as most people think. So in first-order logic, first-order forms, first-order languages, you have a full representation of objects. You can refer to entities in the world. You can also, of course, refer to things that are not in our world, but are maybe in some imaginary world. You have an expressive set of what we might call natural connectives. Most critically, you have logical implication. If something, then something else. And that allows you to say a lot of things in a very natural way. Not everything in a natural way. Logic can get complicated, but it's certainly an important feature to have. And an essential feature to have is quantifiers. We can talk about something being true for all instances of a particular kind of object, and we can also talk about there simply being at least one thing about which a following statement is true. The reasoning is semi-decidable. You could also look that up if you want a more mathematical exploration of what's going on here. But suffice it to say that there are certain problems that will just go off into infinity and never get an answer. And that's not desirable. However, it may not always occur often in practice, especially within the bounds of a particular theory. So is it a deal breaker in terms of the work you're doing? That's something to evaluate, and it takes really some thought to look into this issue and see whether it's actually going to impact you. First order provers now are largely based on superposition calculus. I'm not doing a lecture on that. You can look that one up, or I'll try to maybe get Jeff to do a lecture on it in the future. It's a little complicated, but it was a big advance in theorem proving that basically allowed efficient handling of equality. We'll talk about equality in a moment. And as I said, very mature, fast ATP systems, and there are a lot of first order systems that are quite fast. In this lecture, I'm just going to use E and Vampire. They're the two best, arguably. So here's an example, interesting, fun, silly puzzle example based on the comic strip of Garfield. So Garfield is a cat, Odie is a dog. Cats and dogs are pets. So here we get into the first sort of statement that you can't just say in propositional logic, cats and dogs are pets. So for every instance of a cat and every instance of a dog, they have the property of being pets. So we've got variables and referring to objects in the real world. John is a human. Every pet has a human owner. We can talk state rules. So if a dog chases a cat, then the cat's owner hates the dog owner. And there's proof that we can come out of this set. We don't actually even have to ask anything. We can just ask, is the system consistent? Or you could ask, does John hate himself? And this is another puzzle taken from TPTP. It's online in that set. I did make one modification to clear up the logical statements a little bit, and that's what's shown on this next page. So again, you don't have to understand all of this, but I do just want to point out that we have variables, we have quantifiers, and we also have equality. And these are important mathematical operators in order to talk about our world. We want to be able to say, if something is true, then I can conclude some other new thing. We need to be able to say, here is a property that's true of everything that has some characteristics, and that allows us to conclude something new about the world, about that thing that we've just referred to. We need variables. We need an inference system that allows us to say, well, I have a cat. The cat's name is Garfield, and all cats like milk. Or cats that are owned and domesticated have a milk bowl in the house. Right? We want to be able to make conclusions about things that are denoted in the real world by named terms in a system, so that we can conclude things about specific objects or entities in the world as opposed to just propositions. It gives us an expressiveness that's getting closer, a little bit closer to the expressiveness of human language. And so therefore it forms a language that has some predictive power and it has some utility. It conforms with some things that we know how people reason. Not in all cases, but at least in many cases. It does enough useful simulation of a sort of reasoning that it's valuable as a computational and mathematical system. Again, if we run the system here, I've run it with Vampire instead of eProver, and this is the command I used, and this is the proof that I get, the tree of intermediate inferences all leading to a contradiction that one gets, and so I'd encourage you to try this yourself. An important and somewhat more recent variant of these logics, an extension of these logics, is called typed first-order form with arithmetic. So for many years, I was rather frustrated that for the work that I'm doing with the sumo ontology, I didn't have a prover that could handle numbers and arithmetic. And it turns out it's rather hard to say useful things about the world, to do useful inferences, and not at some point have to worry about adding two numbers together or talking about units or talking about specific calendar dates or times. All of these things require numbers. However, with numbers also comes some risk. So there's famously Russell's paradox that applies often in numbers if you don't also have types. So this paradox was solved in part by creating a type system where these types are disjoint. And so in the TFA system, it's typed and numbers are disjoint from other things, particularly Booleans and other symbols. So this new language, which I've only a few years ago managed to translate my sumo ontology into, is a really wonderful advance. It allows me to say more useful things, and it also allows me to debug parts of the theory that I couldn't debug before. I had for a long time had axioms that use numbers and weights and measures and units. Those things are absolutely necessary. I knew they would be necessary even starting in the year 2000, but until the late 20-teens, I didn't have a system that could actually test all those expressions and see whether they were logically consistent. Turns out there have been a few inconsistencies since fixed, and so now I'm a lot more confident in the power of this overall ontology because I've had a chance to test it with some modern theorem provers, in particular Vampire. There's not a lot of systems that implement the TFA language, and so I really am just using Vampire for this stuff. It's rapidly maturing stuff. Hopefully more people will write TFA as a capability into their theorem provers because I think we really need it to represent reality and do useful things. And it's wonderful that I can do this stuff now. So here's a particular, maybe somewhat contrived example, but it's small enough that I can at least show the input formulas on one page. So a list is Fibonacci sorted if it is sorted, and every element is of greater to or equal to the sum of its two predecessors. I think I need to rewrite this. I've just taken the language from the notes about this problem. All right, so in a Fibonacci sequence, you have 1, 1, then 2, then 3, then 5, right? So each successive number is equal to the sum of the preceding two numbers from the third element onwards. And you can state this in the TFA language. A variant is called TFF. That's what the TFF stands for here, typed first order form. It requires that you have type definitions. I've pointed out a couple of those. Maybe in a later video I'll go into some detailed discussions of the syntax, but here of course I'm just trying to give you a flavor, a sense of the fact that there are these different logics and they have different properties. There are different things you can represent in them, and crucially there are different things you can't represent in certain classes of logics. It's not an arbitrary or aesthetic choice. It's not something you can solve with a markup language or write in a weekend in a database. It's mathematics that's been worked out over a very long period of time. And so if you're not familiar with this mathematics, be very cautious about making statements about what logics can and can't do. There aren't any arithmetic operators in this example. There is sum and product and difference and a number of others that are built in. This example is just showing inequalities. For example, less or greater than or equal here with this $ keyword. You see it in a couple of the axioms. And so you can run these axioms and see whether they're consistent, and you can also maybe create a list of numbers and test whether it's consistent. So that's what we've done in the conjecture. We've created a list that is formed by cons operations as you'd get in Lisp. So my cons of 1, 2, 4, 7, and 100, and you want to see whether that's a valid Fibonacci sequence. It isn't, and so you get a proof by contradiction if you run it through Vampire. And here's the call that you would make, and here's a visual representation of the proof you would get. Lastly, I want to talk about typed higher order form. So this for me is kind of the holy grail. This is what I need in order to represent everything I want to say about the real world, because it removes some critical limitations that I have even in typed first order form with arithmetic. Right? In a first order form, every thing that you quantify over must be an object, an entity. Right? It can't be a formula. And I want to be able to have formulas that I quantify over. And if I quantify over something, that means I can have it as an argument to another relation, a relation that I've created. And we'll see in a moment what some of those, at least one of those useful relations is. Typed higher order form has things like features like lambda calculus, something actually is beyond my competence at the moment. Maybe we can get Jeff to talk about that, or Christoph Bensmueller could come back on the channel, or Chad Brown could come back and talk about these things. It doesn't seem like I need lambda calculus at the moment. I just need the ability to quantify over relations and probably implement something along the lines of Kripke semantics. So this is active research, but there are provers that actually handle this language, and it's just I have to figure out exactly how to translate from Sumo to this particular more complicated language. Christoph Bensmueller and I did a stab at this quite a number of years ago, but it's basically been unfinished work since then. We can do some things, but not a lot of others. Chad Brown has been helping me a lot recently in this area. So hopefully I'll have some good news to report about the research that we've done there, but it's not finished yet. So Jeff has asserted, well, this language is great for mathematics and mathematicians, but not really for regular people. Well, I hope that with some effort, even a regular person like myself can eventually learn this language. The syntax is a little bit complicated and maybe off-putting for some people. It certainly took me a little while to get a handle on it, and I don't claim to have a complete handle on the language, but I think it is possible for people to learn it. It just is going to take some effort to explain, and hopefully videos like this will also get an explanation going that more people can understand. There's very mature interactive theorem proving, and so a lot of mathematicians are working actively with higher order logics. There are logical reasoning systems, interactive theorem provers for higher order logic, like Koch and Hall, and quite a number of others. That's not really my area. I'm more interested in automated theorem proving, where the system can reach a conclusion to a query automatically. But if you're a mathematician trying to prove something novel in mathematics, probably it's not possible to just ask a system to come up with it automatically. You're going to have to lead it by the hand. And so there are these tools that allow a mathematician to partner with the machine trying to find proofs for novel areas in mathematics. There are some ATP systems. Leo now 3, it was Leo 2, Leo 3 by Christoph Bensmueller and Andrew Steen, or Alexander Steen, and I believe a few others on his team have created this Leo 3, which is a great system. There's Chad Brown's Sadillacs, there's Lash that Cesare Kalishik and Chad are both working on, and zipper position is another. There's a lot of work in this area, but it's not certainly as mature as first order logic. So let's look at just a really, really simple example, one that you just can't do in a first order system, at least not as written here. So let's say Bill knows that he's the father of Joe and that he's the father of Jane. And it is the case that Bill is the father of Joe. Bill is also the father of Jane. And we want to ask, does Bill know that he's the father of Joe? Now, you might think that this is trivial, but it requires that I be able to give an entire logical statement as an argument to a predicate. In this case, the predicate knows. I want to have a knows relationship between an agent, Bill, and an entire formula that is Bill is the father of Joe and that Bill is the father of Jane. Now, I could syntactically do this in first order. I could essentially pass the knows relation a list, including a nested list, but then I would not have a proper semantics for the logical operator, the and in between them. If you try to do this logical inference in a first order system, and I'd welcome you to go try it with Vampire and E in the FOF language, and you'll find that it doesn't give you the answer you want. It can do unification over terms, but it can't do inference that preserves the semantics of the logical operators when they are given in a formula that's an argument. So what we want and what we get with a higher order system, we want to be able to ask separately. Well, if we know that Bill knows that he's the father of Joe and that he knows that he's the father of Jane, well, then certainly he knows separately that he is the father of Joe. And so if you run the Leo theorem prover with the command that I have given here, then you get the answer you would expect. You do get a proof. You get a proof by contradiction. It lays out exactly what's going on here, and it's a fairly short proof, right? So I hope this has started to give you a flavor of how there are these different logics, what their limitations are, and why we might want to use more expressive logics. I've alluded to a few things in this talk. I'll put them down in the comments section about videos that I have about contradictions, things like how to represent probabilities, which is another thing, or preferences that you might want to have in your logical system that can be handled in a higher order logic, much contrary to what some people that aren't familiar with more expressive logics might tell you. In fact, this is possible in logic. You just have to pick the right logic. So I hope this was useful to you. Hope you enjoyed it. I'm eager for your comments, and like, comment, and subscribe, all those usual YouTube things, and thanks for listening.